Welcome all to the week 6 problem solving session of the course Fundamentals of Food Process Engineering. In this week, we'll be solving the week's problems regarding the week 6 syllabus, which includes the drying technology. So, in this week, we'll have a mixture of both numericals as well as theory based questions. The theory based questions are pretty straightforward in this particular week, but the numericals will be slightly bit lengthy and a bit confusing as well. So, during this problem solving session, if you guys have any doubts, kindly stop me there via either unmuting yourself or through the in-call messages, and we'll take up that question again. If you're able to answer any question also, do the same. Okay, so question 1, we have two statements. We have to identify whether these are true or false. So statement 1, in a sensible heating process, the humidity of air is constant but the dry bulb temperature increases. And statement 2, in a sensible heating process, the relative humidity increases. So which of these statements are true and which of these are false? So statement 1, any clue whether it is a true or a false statement? Okay, so before we go on to answering that question, we'll first learn the meaning of the terms that are given in the statement. So, humidity is basically the amount of water vapor in air divided by the total amount of air. So, air will have a lot of gases as well as water vapor. So, the amount of water vapor in the air divided by the total amount of air that includes the water vapor as well. So, the amount of air divided by total amount of dry air is known as humidity. So, and then you have relative humidity, the amount of water vapor in air compared to the total amount of water vapor that can exist in that particular temperature. So basically the pressure due to the water vapor in the air at that particular temperature divided by the saturation pressure, that is PV, if you term the PV as the pressure due to the water vapor and PS as the saturation pressure at that temperature. So PV by PS will give you relative humidity. So when we look at this is an example of a psychrometric chart. In the psychrometric chart, at the bottom you will have what is known as the dry bulb temperature. That is the temperature that you get upon measuring with the help of a thermometer. So you have a dry bulb temperature, and in the y-axis in one end, so in the y-axis you have what is known as humidity here. So, and in a sensible heating process, the A to B here shown here is an example of a sensible heating process. So as you can see here, in a sensible heating process, you are increasing the dry bulb temperature. As you can see here, it is going all the way from somewhere around 33 degrees Celsius to 70 degrees Celsius. So you are increasing the dry bulb temperature. But if you look at the y-axis is pretty much the same. There's no, you are not going up, you're going only parallel to the x-axis. So the humidity of the air remains constant, but only the dry bulb temperature increases. So this is an example of a sensible heating process. So statement 1 is true. A to B, the temperature rises, but the absolute humidity here remains the same. So apart from absolute humidity, you can also find certain lines that are curved here. You have multiple lines that go in a curved manner. So these curved lines indicate the relative humidity lines. So here you can see this is 10%, 20%, 30, 40, 50 like this. So each of these curved lines represent the relative humidity. So if you go from A to B, A is at 100% relative humidity line. But if you go from A to B, it goes all the way to 20% relative humidity line. You can see that the B lies in this particular curved area. So always in a sensible heating process, your relative humidity will decrease from 100%, it is going all the way till 20%. So the relative humidity decreases. So statement 2 is false. Hope this is clear. When you imagine a psychrometric chart, you'll be able to understand what a sensible heating process is. So A to B is a sensible heating process. On the other way, had you gone from B to A, it will be a sensible cooling process in which the dry bulb temperature will decrease, but your absolute humidity will still remain the same and your relative humidity will increase. So A to B is sensible heating, B to A is sensible cooling. So here in this case, the humidity remains the constant. Humidity remains constant, dry bulb temperature increases and relative humidity decreases. From 100% it is going to 20% here. So this is just an example. You can grow from 80 to 10 as well, it doesn't matter. The answer here is option A. Is this clear? So these lines, these curved lines are relative humidity lines. These diagonal lines that you see are the enthalpy lines. It's going all the way from here to here, if you can see. So these are enthalpy lines. These curved lines are relative humidity lines. And the y-axis here is the absolute humidity. And the x-axis here represents the temperature. So if there's any doubt in looking up at a psychrometric chart, please let me know. Because there might be problems where you will be given a certain dry bulb temperature and you will be given the relative humidity and you will have to calculate what is the absolute humidity from a psychrometric chart. I'm not sure if it is still, that would be a part of your examination question, but in the videos that has been discussed in the in this particular week, we have certain problems where you will have to look up into the psychrometric chart and then figure out what is the absolute humidity of certain cases. Okay, moving to question 2. The statement 1. Puff drying is accomplished by exposing a relatively small piece of product to high pressure and high temperature for a short time, after which the product is exposed to atmospheric pressure. And statement 2. The products produced by puff drying have very low porosity with slow rehydration characteristics. Which of these statements are true and which of these are false? So any clue what a puff drying process is? So puff drying process is often used for fruits and vegetables where you want to dry those fruits and vegetable products. So in the puff drying, yes, it is accomplished by exposing a relatively small piece of the product. You have cut slices of fruits and vegetables. You have relatively small pieces of the product that is exposed to high pressure and high temperature for a short time. And after that, immediately the product is moved to the atmospheric pressure. So in this case, what happens is that since you are first exposing the product to very high pressure and then immediately bringing it back to the atmospheric pressure, you will often have an expansion of the product happening. So your product will start expanding, and because of this expansion, which is why it becomes like a puffed like substance. So because of this expansion, these products have very high porosity. You will have a lot of pores, tiny pores in it with rapid rehydration characteristics. Because there are a lot of pores in these products, the moment you add water or you expose it to moisture, these pores will help in rapidly taking up that moisture content. So when the product is moved from a high pressure to an atmospheric pressure, the product puffs and expands, and upon this expansion you will have pores forming in the product, and once you expose it to moisture or water, it will have very rapid rehydration characteristics because of these pores. An example of this technique is for using for fruits and vegetables. So statement 1 is true, but statement 2 is false. It will have a high porosity and a faster rehydration characteristics. So answer is option A. Any doubts so far? Okay. Moving to question 3. Drum dryers are used when A. The material is too thick for the spray dryer and too thin for the rotary dryer. B. When the material is too thick for the rotary dryer and too thin for the spray dryer. C. When the material is non-biodegradable, and D. When a large crystal size is to be obtained. So, any clue what the answer is to this question? So, before we proceed, what is a drum dryer? So you have 3 types of dryers that has been introduced in this question. So first we look at the drum dryer that has been asked. So a drum dryer looks like this. You will have a rotating drum and the inside of the drum will be sparged with steam. So you will have steam at the inside of the drum, and on the outside of the drum you will have your feed that is being made into a thin film on the surface of the drum. So the inside of the drum will have steam. Then you will have the drum surface, and on the outside of the drum surface you will have the feed being coated into a thin film. So, and this during the process the drum keeps rotating. So because of the steam that is being sparged inside the drum, your thin film will start becoming dry, and after a certain rotation, after a certain length of rotation, you will see that the film starts to dry up. And once the film has dried, you will have a knife or a scraper that will scrape out the dried film, and then you will be collecting the product at the other end. So majorly the drying process is because of the conduction, because the steam will first heat up the surface of the drum and then it will start heating up the product that is laid onto the surface of the drum. So this is an example of this is how the drum dryer works. So as you can see here, your food product has to be thin enough to be spread into a thin film. If your product is too thick, then you will not be able to make it into a film and you will have uneven drying. So only certain products are suitable for drum dryers, which are not too thick and not too thin. Whereas in case of a spray dryer, if you see, as the name suggests, you will have a large chamber which often will be under vacuum or under very low pressures. So your product will be sprayed through a nozzle or an injector into tiny droplets, and these tiny droplets will be quickly dried in the drying chamber. So for a spray dryer to work, your particle size has to be very small and your food has to be very thin so that it can be made into particles. So a spray dryer you will end up having products of micrometer size. So your product will be very thin, your food product will be very thin. You will spray it into tiny droplets, that droplets will dry and then you will collect the product. So for a spray dryer you need very thin material. Whereas on the other hand, for a rotary dryer basically looks like a very long cylinder that is inclined. You will have a very long cylinder like this, and then one of them will be one region will be inclined, the other region will be a bit lower. So you will feed the product at one end and you will keep rotating the drum or the dryer, and as you rotate, the product will fall from one end of the cylinder to the other end of the cylinder and it will keep drying during that falling process. So for a rotary dryer, you want your product to fall, so it will be much more thicker, the material will be much more thicker, whereas for a spray dryer the material will be much more thinner. And when you have a product in between these two, you will require a drum dryer. I hope this is not confusing. You need a thin material for a spray dryer, a thick material for a rotary dryer, and drum dryers are between these two. So they are used when the material is too thick for a spray dryer that you cannot make it into droplets, but it is too thin for a rotary dryer to fall through that cylinder and get dried. So when you are able to make a thin film out of the food particles, then you can go for a drum dryer. So the answer is option A. Any doubts so far in these three dryers? The mechanism of action? So if you Google the name of spray dryer and rotary dryer, you will have Google images coming up that will be more easy for you to understand. And also the rotary dryer has been explained, rotary dryer and spray dryer are explained in the video lectures as well. So you can go through those. Okay, if there are no doubts, we'll move on to the next question. Statement 1. The wet bulb temperature is defined as the temperature measured by a thermometer whose bulb is covered with a wet cloth. And statement 2. The dew point temperature is the lowest temperature attained when a mixture of air and water vapor is sensibly cooled. So in this case, yes, statement 1 is true, because when you measure the temperature of certain... is there any doubt? Any part?
No doubt. One answer is both are true. C.
Yeah, the answer is C. So in a wet bulb, this is the dry bulb where you do not have any wet cloth surrounding the bulb. This part is known as the bulb. So when you measure the temperature of the air directly via a thermometer, it is known as the dry bulb temperature. When you surround the bulb with a wet cloth, you will have an equilibrium maintained between the cloth, now the moisture in the cloth, and then the atmosphere. And with this equilibrium, you will measure the temperature, and that is known as the wet bulb temperature. So yes, statement 1 is true. And statement 2 is the dew point temperature is the temperature at which the water vapor in the air almost starts condensing. So that is the lowest temperature where you will have a mixture of both air and water vapor. If you try to reduce the temperature further, then all the water vapor will start condensing into liquid. So that is the lowest point at which you can have a mixture. So the dew point temperature is the temperature at which this water vapor in the air starts condensing, and hence statement 2 is also true. So if you look here, this is an example, again an example of a psychrometric chart. Here the relative humidity lines are not there. If you can see, the curved lines are not there. We only have the enthalpy lines, the dry bulb temperature, and the moisture content here. So if let's say my dry bulb temperature is somewhere at around 47 degrees. So at 47 degrees, and my moisture content is somewhere close to 0.09. So let's say this is where my condition prevails right now. And how you calculate wet bulb temperature is that you draw a line parallel to the enthalpy lines here. So the enthalpy lines are diagonal in nature. So you draw a line parallel to these enthalpy lines diagonally. And when it hits the 100% RH line, which is here, you drop it down, and this is your wet bulb temperature. So you, from your existing point, draw a line parallel to the enthalpy lines, reach 100% RH, and then drop it down. This will be your wet bulb temperature. In case of a dew point temperature, you draw a line parallel to the x-axis, reach the 100% RH line, and then drop it down. So this will be your dew point temperature. So hope this is clear how to calculate wet bulb and dew point, and what is the difference between those two. Answer is option C here. Okay. Question 5. If there is any doubt, please stop me. We'll repeat that question again. So in osmotic dehydration, the solutes used are generally dashed with fruit slices or cubes and dashed with vegetables. A. Sugar syrup or sodium hydroxide. B. Sodium chloride and corn syrup. C. Sodium chloride and sugar syrup. And D. Sugar syrup and sodium chloride. Any clue what the answer is? It's pretty straightforward and very logical answer as such. So how do you dry up a fruit slice and how do you dry up a vegetable slices. So in on osmotic dehydration type, which is also one of the drying technique, we partially remove the water from plant tissues, either vegetable tissues or fruit tissues, by immersing them in a hypertonic solution. So a hypertonic solution consists of a concentrated form of solute. You will have very high concentrations of the solute in a hypertonic solution. So the in this case, what you'll do is you will immerse these fruit or vegetable slices in highly concentrated form of a solution. So in case of fruits, it's generally a sugar syrup which contains high concentration of sugar. And in case of vegetables, we immerse it in a solution containing high concentrations of sodium chloride. So because of the high concentrations of the solute on the outside, in order to maintain an osmotic balance, the water from your inside of the plant tissues will come to the outside solution. Basically, osmosis is what is happening. Your outside solution has less amount of water and high amount of solutes. Inside the tissues, you will have high amount of water. So in order to maintain an osmotic balance, water will move from the tissue into the outside solution. Now since water is moving from the tissue to the outside solution, you will automatically have partial removal of water or something known as dehydration. So here it's only the water molecules that are moving out. So you will have all your vitamins, minerals, colors, flavor and taste intact in those fruits and vegetables. So this is one of the advantage of this technique. There is a partial removal of water from the plant tissues by immersing it into a hypertonic solution. There is a high retention of vitamins and minerals, color, flavor and taste. And in osmotic dehydration, the solutes generally used are sugar syrup for fruit slices and salt or brine for vegetables. Answer is option D. Hope this is clear as to how osmosis works. The water outside in the solution will be very less, water inside the tissues will be more. To maintain an osmotic balance, water will move from inside of the tissues to the outside solution, hence resulting in dehydration or drying. Okay, question 6. The moisture content at which the constant rate period ends and the falling rate period starts is called A, the equilibrium moisture content, B, free moisture, C, intermediate moisture and D, critical moisture content. So which of these is the correct answer? So before we discuss what is the correct answer, let us look at what a drying rate, how a drying rate changes. Sorry?
D.
Yeah, the answer is D. But before we move on to the answer, let us first discuss what a drying rate, how a drying rate changes with moisture content, and then we'll move on to the answer. So here we'll start from point A. So let's say your product has certain amount of free moisture in it, and as the drying rate starts, you will see that as the drying starts, you will first see an initial increase in the drying rate. At this stage, generally often you will often see the temperature rise also. So here the temperature rises and the drying rate kind of slowly increases. After a certain time, from B to C, you can see a constant drying rate. This is because your surface is saturated with that water that needs to be dried. Let's say you have a spherical particle in hand, a food product, and the surface is very wet with all the water content. So when you start the drying process, you will have a constant rate, that is, you will have enough water to continuously keep on evaporating it into a water vapor. And once the surface is getting evaporated, whatever water was inside of the particle will diffuse to the outside. So you will have a continuous supply of water from the inside of the particle to the surface, and from the surface also it will be continuously evaporating. So the rate of diffusion from the inside of the particle will often be equal to the rate of evaporation. So you'll have a very saturated surface with a surface saturated with water that needs to be evaporated, which is why you will have a constant rate. There is nothing limiting the evaporation at all, or the drying process at all. So you'll have a constant rate. After a certain moisture, as you can see here, the moisture is continuously decreasing throughout. So at a certain stage known as the critical moisture content, you can see that the constant rate ends and the falling rate starts. This is now because whatever water was there in the surface has now evaporated, and it is getting more difficult for the water to come from the inside to the surface. So if you can imagine, as you dry a certain particle, the particle will start forming, will start becoming hard, the pores will start closing, and it will become pretty difficult for the water to diffuse from the inside to the surface. So now, since the water is having very difficulty going from inside of the particle to the surface, now there is no more water to rapidly evaporate. So your rate will automatically start falling. Even if there is very less moisture now to evaporate, since it's not diffusing to the surface, or it is unable to diffuse to the surface where you have that hot air supply, your drying rate will start falling. And after a certain point, it often happens that from C to D you can often find a linear decrease, and after D to E there's much more difficulty in the water coming to the surface. You will have a lot of other factors that are limiting, like diffusion, capillary action and all. Because of that, you will see a further decrease in the drying rate all the way till the point E, which is known as the equilibrium moisture content. So this is how a drying rate varies with moisture content. First, you will have a constant rate where the rate of diffusion from the innermost particle region to the outer surface is equal to the rate of evaporation. After a certain stage, when it reaches the critical moisture content, you will see that the diffusion is now limiting the process, and hence you will start to see a decrease in the drying rate. And those can be two phases. There will be a phase 1 of falling rate and then a phase 2 as well. So the answer here is that the critical moisture content is the average material moisture content at which the drying rate begins to decline. So the answer here is option D. So a more clear explanation is given in the next slide, which is also related to the drying period. So after critical moisture content dash starts: A, the saturated drying region; B, the unsaturated drying region; C, constant drying region; and D, none of the mentioned. So it's the continuation of the previous question. So what is the answer for this? So here, as you can see, we know that after the critical moisture content, the falling period starts, and this falling period is known as the unsaturated drying region, because your surface is no longer saturated with water. The water is finding it difficult to come from the innermost particle region to the surface. So since the water is finding it difficult to come to the surface is no longer saturated with moisture. So the falling rate is actually known as the unsaturated drying region. So in order to have a much clear explanation of what I was explaining before, the moisture content at the end of the constant rate period is known as the critical moisture content. At this point, the surface of the solid is no longer saturated, and the rate of the drying decreases with decrease in moisture content. So at point D, the surface moisture film has fully evaporated, and with further decrease in the moisture content, the drying rate is controlled by the rate of the moisture movement through the solid. That is, the water has to pass from the center of the solid to the surface of the solid. So it is entirely controlled by this transfer of moisture from the innermost region to the surface. from point D to E represents the conditions where the drying rate is largely independent of the conditions outside the solid. So after this, no matter how much you increase the temperature of the dry air that you are sending to dry the particle, or how much ever humidity you send it in, it does not matter, because what is limiting right now is the water movement from the innermost particle to the surface. So the moisture transfer may be any combination of the liquid diffusion, capillary movement and vapor diffusion. So all these processes, either one or all of them combined, could limit the moisture transfer from the center to the surface. So you see a much more drastic drop in the drying rate from D to E. And the reason why it is known as unsaturated drying region is because the surface is no longer saturated with water as it was in the constant rate process. So hope this is clear. Any doubt in the drying curve? So point C is where there is a critical moisture content, and point E is often the equilibrium moisture content. It can either be 0 or it cannot be 0. It need not necessarily pass through the origin. But the equilibrium moisture content is where the drying rate drops to 0. But it's not necessary that you will end up completely removing all the moisture. Okay, so we'll now move on to small numericals and we'll then take up bigger numericals. So potatoes, question 8, potatoes are dried from 14% to 93% of total solids. Considering 8% peeling loss, the product yield from 1 ton of a raw potato will be A 10.56%, B 13.85%, C 15.25% and D 20.58%. So how do you proceed with the question? So this is a basic mass balance problem. So the yield, we will first look at the given. The initial amount of potato that we have is 1 ton or 1000 kgs, and it is given that you have 8% peeling loss. So what you do is you take a raw potato, you peel it first and then dry the potato. So if you have 8% peeling loss, which means that only 92% is remaining with you, the rest 8% is lost. So the amount of potato that is left after peeling is 0.92 into 1000, which is 920 kgs. So only this 920 kg is going to go to the dryer. And we can always do a solid balance. We cannot do a moisture content balance because it doesn't make sense. You'll have a lot of losses, but your dry solid will remain the same. So we do a solid balance generally. So let's assume that F is the amount of feed potato that you're sending inside the dryer, and this feed potato will have both moisture content as well as the dry solid, and MDF is the dry mass, that is only the potato, not the water vapor or not the moisture. So MDF is the dry mass in the feed. So F into MDF will only give me the dry potato's weight, not the potato that includes the moisture content. Hope this is clear. And that is equal to P, which is the total amount of product that is leaving the dryer. This P will again include the dry potato as well as some remaining moisture content that is still there. There is nowhere mentioned that you are not getting 100% total solids, which means there is still some amount of moisture left even after the drying process. So this P will include the total mass of the product that includes the moisture content as well as the dry solids, and MDP is the dry weight of the potato that does not include the water vapor or the moisture content. So basically you are doing only the solid balance for the dry weight, not the moisture content. So F is given here as 920 kgs. MDF is given as 14%. So you have 14% total solids when it enters the dryer. So MDF is 0.14. We don't know what P is. We don't know how much potato is coming out, because you will have a lot of loss in moisture content also. So the P will change. It will not remain 920. You will have some amount of water vapor that has evaporated. So P will change, and MDP is the total amount of dry solids of the product that is coming out, which is 93% or 0.93. So from there you can get P as 138.49 kgs. So when you send in 920 kgs of potato, what you get out after evaporating so much is only 138.49 kgs, which still includes some amount of moisture content. So in order to find the yield of the product, you take yield is equal to potato dried by potato that is sent into the dryer or potato that is utilized, which includes 138, which is 138.49 divided by 1000. So you start with the potato that you first initially took. So you will include all the peeling losses as well. You took 1000 kgs of potato, but you ended up having only 138.49 kgs, which means the total yield of the process is only 13.85%. So hope this is clear. Any doubts in this? Any doubt as to why P is different from F? Any doubt, kindly let me know, because this is the simplest of the problems that we have. The mass balance kind of questions are the simplest that we have. We'll then further on increase the difficulty of the problems as well. The answer is option B. So this is just the basic mass balance of the dry solid present in the potato. Moving to question 9. In a dash drying method, agents like glycerol monostearate, egg albumin and protein isolate are used. So you have A, spray drying, B, fluidized bed drying, C, foam mat drying, and D, puff drying. So which is the correct answer for this question? So we already discussed what spray drying is. You just have a very thin material and you will pass it through an injector or a nozzle that will spray it into tiny droplets. Those tiny droplets will dry up. In a fluidized bed drying, you will have all your particles inside a column and you will pass air through the bottom at a certain velocity such that the particles will behave like a fluid. It will become like a fluid like material where it will keep bouncing off because of the air that is coming from the bottom. And see, you have foam mat drying, which is where you will add agents like glycerol monostearate, egg albumin and protein isolate. So all these three kind of materials are materials that often give froth. So if you take a protein isolate or an egg albumin and vigorously shake it or agitate it, you will often see a foam like substance or froth like substance that is being formed. And these froth like foams are pretty stable. They don't break down or so because of the presence of these agents. So what you do is you mix your food product with these kinds of agents and you continuously agitate it or so or whip it to form a foam mat, as you can see here. And then this foam mat will be subjected to drying. And this is often preferred because of the foam you will have a lot of a foam is much more easier to dry because you will have tiny pores in it that will increase the liquid gas interface. A froth is much more has a lot of air trapped in it, and this will increase the liquid gas interface and it will increase the rate of drying as well. So in a foam mat drying, you will add these agents to create a foam and stabilize it. Then you dry the foam so that you get a particle, a powder like this. The answer is option C. And puff drying is something that we already discussed in the previous slides. Okay, moving to question 10. If there's any doubts in any of the previous question or anything that needs to be repeated, please let me know. So in a grain drying system, the air at 25 degrees Celsius is heated to a temperature of 75 degrees Celsius to dry the grain. The dry bulb temperature of the air drops to 60 degrees Celsius while passing through the grain dryer. The heat utilization factor of the drying system is dash. So you first heat up the ambient air from 25 degrees Celsius to 75 degrees Celsius, and this hot air you pass through the dryer. Now because you pass the hot air through the dryer, the moisture that was initially present in the food will now be taken up by the air, and because of this the humidity of the air will increase, and the dry bulb temperature will drop to 60 degrees because the water is now there's more amount of water present in the air. So from this we have to calculate the heat utilization factor. How do you solve this question? Okay, first look at the given here. Let's take T1 as 25 degrees Celsius, which is the initial temperature of the air. T2 is the heated temperature of the air, which is 75 degrees Celsius. And T3 is the temperature of the air that comes out of the dryer, which is 60 degrees Celsius. So the heat utilization factor, or HUF, is defined as the drop in the dry bulb temperature of the drying air, that is inside the dryer, what has been the drop in the temperature, divided by the rise in the dry bulb temperature of the ambient air, that is the air that you are sending inside the dryer. So drop in the temperature during the drying divided by rise in the temperature before drying, which is basically T2 minus T3. So T2 is the hot air that you are sending in, and T3 is the temperature to which it has dropped because of the drying. So T2 minus T3 will give you the drop in the temperature due to the drying process. The rise in the dry bulb temperature is because of the heating that you have done before entering it into the dryer. So you are increasing the temperature from T1 to T2. So the rise in dBT is T2 minus T1. If you just substitute the values, 75 minus 60 degrees, which is the drop in dry bulb temperature, divided by 75 minus 25, which is the rise in the dry bulb temperature due to heating. This gives me a heat utilization factor of 0.3. So answer is option C. So this is how you define the factor known as heat utilization factor. Any doubts so far? Okay. Question 11. Calculate the EMC of paddy at the relative humidity of 22% and temperature of 45 degrees Celsius using the Henderson equation. And given C is equal to 9 into 10 power minus 6 Kelvin inverse and N equal to 2. So EMC is basically equilibrium moisture content. If you remember the drying curve, EMC is where your drying rate has completely dropped to 0 and the moisture content is now in equilibrium with the surroundings. The moisture content at which the substance is now in equilibrium with the surroundings and your drying rate has completely dropped to 0. So there are multiple empirical formulas and equations that help you to determine the EMC of a particular product, given that you know certain parameters. So in this case, for a Henderson equation, all you need to know to calculate the EMC is the relative humidity and the constants of the Henderson equation and the temperature. So given the relative humidity is 0.22, the temperature given, where I'm converting it into Kelvin, which is 45 plus 273, which is equal to 318 Kelvin. The constant C is given as 9 into 10 power minus 6 Kelvin inverse, and constant N is equal to 2. Now the Henderson equation, which is useful for calculating the equilibrium moisture content of a product, is given by 1 minus RH equals to exponent of minus C into T into EMC power N, where RH is the relative humidity, C and N are constants, T is the temperature, and EMC is the equilibrium moisture content that we need to figure out in this question. So this is just basic substitution of the equation. You just need to know what a Henderson equation is. So I'm just substituting the values here. 1 minus 0.22 is equal to exponent of minus 9 into 10 power minus 6, which is C, into temperature in Kelvin, which is 318, and EMC per square. So I'm taking a natural logarithm on both the sides to remove the exponential. So ln of 1 minus 0.22 is equal to 9 into 10 power minus 6 into 318 into EMC square. So from this, I am getting EMC square is equal to 86.81. So EMC, you will get it directly in dry basis, which is 9.32%. The answer is option A. Hope this is clear what a Henderson equation is. There are multiple other equations also, and you will get those equations in the lecture videos that has been discussed this week. Okay, question 12. A food dryer has a drying constant of 8.33 into 10 power minus 3 minute inverse in the following rate period. The EMC of the food material is 4% by dry basis. Then the time required to dry the food material from 60% to 10% moisture content dry basis is so many minutes. So here we look at the given. The drying constant, we are looking at a falling rate period where we'll assume it to be linear. If you remember the drying curve, after it reaches the critical moisture content, you have a falling rate period that happens. So that can either be linear or it can be non-linear as well. In this particular case, will be, if not mentioned otherwise, you will assume that the drying period is linear in nature. So if you are looking at linear dependence, so for during the falling period, TF is equal to WXC minus XC by ARC into ln of X1 minus XC by X2 minus XC. So we'll discuss what each of these stand for, where W is the weight of the product that needs to be dried, XC is the critical moisture content, XE is the equilibrium moisture content, X1 is the initial moisture content of the particle before it has started drying, and X2 is the final moisture content that you desire to have, and A is the area, and RC is the rate per area. Is the drying rate per area. And what you need to understand is that all these moisture contents are in the dry basis, are on dry basis or dB as mentioned here. If you have a problem where it is given in wet basis, you need to convert the moisture content into dry basis and then substitute it inside this formula. So this is clear. So in this case, if you look at the equation, we only have XE, which is 4%, which is the EMC here. You have the initial moisture content, which is X1 as 60% and X2 as 10%. We do not have any of the other parameters here, but you have something known as the drying constant. The drying constant is actually this entire thing. K is equal to ARC by WXC minus XC. So this is the drying constant, and there it is mentioned here as K. So now you have the drying constant, you know what is X1, you know what is X2, you know what is XE. So since it is already given in dry basis, we need not convert anything. XE is 0.04, x1 is 0.6, x2 is 0.1, and k is given as 8.33 into 10 power minus 3 minute inverse. So this is just a basic direct substitution. So I'm substituting k as 8.33 into 10 power minus 3, x1 is 0.6 minus xe which is 0.04, x2 which is 0.1 and xe which is 0.04. So when you substitute and calculate the values, you get time is equal to 268 minutes. This is option B. Hope this is clear, the formula given here. So this is only when you assume it to be of a linear dependence. So, and this is only for the falling period, not for the constant period. For a constant period, you have a different equation. And when you are asked to calculate the total amount of drying time, you will have to sum up the time due to the constant period plus time due to the falling period. So we will do a similar question in the later slides. But as of now, I hope this is clear. If you guys have any doubts, kindly let me know. We will go through that part again. Okay, question 13. Which of the following dryer is used for production of instant coffee and coffee powder? You have A. spray dryer, B. fluidized bed, C. rotary dryer, and D. tunnel dryer.
Answer A.
Yeah, the answer is A. Because your coffee can be a pretty, it's not a very thick material. Your coffee with liquid is not, dissolved in liquid is not very thick material. So you can actually pass it through an atomizer or a spray nozzle where you will spray it into tiny droplets, and in this chamber you will have the drying gas that is being passed, and this drying gas will dry all the droplets, and then you will get a fine powder that is collected here, and the rest of the drying gas will be passed through the exhaust. So this is the entire concept of a spray dryer, and it's often used for milk powder, instant coffee, coffee powder, and so on. Basically any material that is very thin and can be made into droplets. So the spray drying involves the atomization of a feed solution or slurry into droplets, followed by rapid evaporation of the droplet by a hot drying gas at a certain temperature and pressure. So since you have broken down the feed into small droplets, it has a much more faster evaporation rate than drying it as a just like that in as bulk material. So you will have a much more rapid evaporation rate, and you will collect the particles at the particle collector. The answer is option A. Question 14. So this is one of the bigger questions that is often being continuously asked. It is part of both your previous year question, and is also in the video lectures as well. So the food product is dried in a pan of 0.2 meters into 0.24 meters into 0.02 meter using air flowing at a velocity of 3 meters per second perpendicular to the drying surface. So you have a pan where you have a food product. So the length into breadth into height is given here. So your area of evaporation is only length into breadth, because that is where you are laying down the food product. So if you completely fill the pan with the food product, that is what you are assuming, then the area of evaporation will be length into breadth here. And the temperature and the humidity of the incoming air is 48 degrees Celsius and 0.014 kg of water per kg of dry air. The wet bulb temperature of the air is 22 degrees Celsius. The humidity and the latent heat at the wet bulb temperature, TW stands for wet bulb temperature. So the humidity and the latent heat at TW is 0.024 kg of water per kg of dry air and 2410 kJ per kg respectively. We need to calculate the total rate of evaporation, assuming that the heat transfer is only due to convection. So when this is the condition where the heat transfer is only due to convection, first we look at the given. The dimensions of the pan are 0.2 meter into 0.24 into 0.02 meter. Velocity is 3 meter per second, and what you need to understand that it is going perpendicular to the drying surface. The direction of the air velocity matters in all these numericals. So you will have a different answer when the air is flowing parallel to the surface. You will have a different answer when it is going perpendicular to the surface. The temperature of the inlet air is given in 48 degrees. I am converting it into Kelvin. So 48 plus 273 is equal to 321 Kelvin. The humidity of the incoming air is 0.014 kg H2O per kg dry air. So once you dry up your food product, the air that is going out will always be at the wet bulb temperature. So unless and until mentioned otherwise, your outlet air will always be at the wet bulb temperature. So the humidity of the outlet air is given, which is 0.024 kg of H2O per kg dry air. Your lambda, which is your latent heat, is given as 2410 kilojoule per kg, because that is what you are supplying to the you have the latent heat because your water is getting converted into water vapor, so you have latent heat as well involved in it, so which is 2410 kilojoule per kg, and you need to calculate what is the total rate of evaporation if you assume that only convection is happening. So in this case, where only convection is happening and you are assuming that the rate is constant here, so in this case the RC is equal to H into T minus TW by lambda. This is when convection is happening and you are assuming to be a constant drying rate, where H stands for the heat transfer coefficient, T stands for the inlet temperature of the air, TW stands for the wet bulb temperature, and lambda stands for latent heat. So, but RC is not the dry heat transfer rate that is asked here. RC will generally have the units of the rate divided by area. So when you have RC, you generally have to multiply it with the heat transfer area in order to get the actual rate. Hope this is clear. So we'll move on to the question. So we already know what is T, which is 48 degrees. We know TW, which is 22 degrees. We have the lambda here. But what we don't have is the heat transfer coefficient. Now the heat transfer coefficient can be calculated if you know the mass flow rate of your air. If you know the mass flow rate of your air, there are other empirical equations that help you to calculate the heat transfer coefficient of the air if you know the direction of the air as well, and if you know the velocity of the air. So how do you calculate H is what we are going to look into. But before we calculate H, we need to calculate what is the humid volume. Yeah, is there any doubt? If there is any doubt, anything that needs to be repeated, kindly let me know. Okay, you first need to, in order to first calculate what is the heat transfer coefficient, the first step is to find out the mass flow rate. So in order to find the mass flow rate, you need to know what is the humid volume. This is the standard equation to calculate the humid volume of air. It's equal to 2.83 plus 4.56 into H, where H stands for the humidity of the air, into 10 power minus 3 into T plus 273. So here we calculate the humid volume of the air at the inlet condition. So here you will substitute temperature as the 43 degrees that is given, 48 degrees that is given there, and the humidity at 48 degrees. So when you substitute the humidity at the 48 degrees and the temperature as 321 Kelvin, so which is 2.83 plus 4.56 into 0.014 into 10 power minus 3 into 321. So when I substitute the values and calculate, I get a humid volume as 0.9289. From this humid volume, the next step to do is to calculate what is the density of air, which can be calculated as 1 plus H by V, where H stands for humidity and V stands for humid volume. So So if I substitute the values again at 48 degrees, you have 1 plus 0.014, which is the humidity value, and the humid volume that you just calculated as 0.9289. This gives me the density of air as 1.0916. You cannot just, generally the density of air is close to 1 only, but you cannot assume that way. You need to calculate via the volume, humid volume, and then you calculate the density of the air, because there will be slight variations and that will affect your answer drastically. And the mass flow rate here, G, is given as velocity into density of air. So this is the formula for the mass flow rate that will help you to calculate the heat transfer coefficient. So in order to know the mass flow rate, you need to know what is the density of the air, and in order to know the density of the air, you need to know what is the humid volume. So when the heat transfer coefficient is not given in the question, first you do is to calculate the humid volume. From there you calculate the density. From the density you calculate the flow rate. So this is not exactly the flow rate. You will have it divided by area. So it is 3 meter per second into 1.0916, which will give you the value in kg per meter square second, which is given as 3.2748 kg per meter square second. This is the flow rate per unit area. I am converting it into hours, so I am multiplying it by 3600, which gives me 11,789.28 kg per meter square hour. So this should be the units in which you substitute it inside the empirical equation that we will be discussing for below. So for when you have the direction of the air perpendicular to the food product, this is the equation that you use. For the equation where you have a parallel flow, you have a different empirical equation that is given in the video lectures. So when you are solving these problems, kindly look into what is the direction of the air that is flowing. And when you substitute G here, this should be the units. So even if you get it in kg per meter square second, kindly convert it into kg per meter square hour and then put it inside the empirical formula. I hope till this it is clear. I know these are all new formulas, but this question has been continuously repeated in the previous year. So I am substituting the value of G here, 1.17 into 11,789.28 raised to 0.37, and the value that you get will be in SI units. Because this is an empirical equation, you will get it in SI units, which comes out to be 37.55 watt per meter square Kelvin. I hope till here it is clear. Calculate humid volume, calculate density, from there calculate the flow rate per unit area. From the flow rate, convert it into per hour scale, per hour units. Substitute that into the empirical equation between H and G. So now you have the heat transfer coefficient that is required in the question. From there you can just directly substitute, where you are substituting H as 37.55 into T minus TW. T is 48 degrees, which is 321 Kelvin, minus your bed bulb temperature, which is 295 Kelvin, divided by your latent heat of vaporization, which is 2410. It is in kilojoules, so I am converting it into joules by multiplying it into 1000. And since the question here is in kg of H2O per meter square hour and not in meter square second, I am multiplying here into 3600. If the options are given in meter square per second, you don't have to multiply the 3600. Since it is given in hours, I am converting seconds into hours here by multiplying it into 3600. So hope this is clear. This is basically H into T minus TW by lambda. All of these converted into HI units and converted into hours scale. So here you have RC. As you can see here, this is not actually the rate. This is rate per unit area. So you need to multiply it into the rate of area of evaporation to get the actual rate in kg per hour. So the actual rate is equal to RC into the cross-sectional area or the area of evaporation, which is your length into breadth. So I'm substituting rate as 1.4584, which we got in the previous slide, into the cross-sectional area, which is length into breadth, which is 0.2 into 0.24. This gives me the actual rate in kg per hour, which is 0.07 kg per hour. Answer is option D. Is there any doubt in this? First step is to calculate H via the empirical equation. Substitute it, you will get it in SI units itself directly from the empirical equation. Substitute it in the formula where you will get RC. RC is generally in kg of H2O per meter square R, which is basically rate per unit area. So you multiply it into the area of evaporation to get the actual rate in kg per R. So this is one of the difficult numericals that you will find in the current week. Okay, so I'll be uploading these PPTs soon enough, so you can just go through these, and if there is any doubt, you can let me know. Question 15. Calculate the total time required to dry a product from 35% to 12% moisture wet basis in an industrial dryer, while 2.25 kg of dry solid per meter square surface area is exposed to the hot air. The drying rate remains constant up to 16% and the EMC is 4%, both of them are wet basis. And the constant drying rate is given as 5 kg of H2O per meter square hour. So we need to find out the total time. As you can see here, we are drying a product from X1, which is 35%, to X2, which is 12%. But it is given here that the drying rate remains constant only till 16%. So if you remember the drying curve, the critical moisture content is the moisture content till which your drying rate remains constant. If you go below this moisture content, your drying rate will start falling, and your falling period will start. Which means if you are saying that the drying remains constant only till 16%, then this is your critical moisture content. It's not directly given here, but you need to understand what the drying curve is to find out what is the critical moisture content here. So from 35% to 16%, you will have a constant drying rate, where 16% is your critical moisture content. When you go from 16% to 12%, you will have the falling rate period. So when you calculate the total time, you need to calculate the time due to the constant rate period plus the time due to the falling rate period. So both of them you will add, and then you will calculate the total time. So again, this is just to brush up. You have X1 here, let's say at 35%. It goes all the way till 16%, which is your critical moisture content. Then it drops to X2, which is your 12%. X1 is 0.35, X2 is 0.12, XE is 0.16 and XE is 0.04. What you need to, again, I am reiterating, these are all in wet basis. And when you are substituting the parameters into the drying rate formula, all of those need to be in dry basis. So you will be converting all these wet basis moisture content into dry basis. And apart from that, what is given in the question is weight per unit area, which is W by A, given as 2.25 kg per dry solid per meter square. And the constant rate drying here is given as 5 kg of H2O per meter square R. So if you remember from the previous question, this is RC. So given this, the total time of drying is equal to the time during the constant drying period plus drying during falling period. So for the constant drying period, this is the equation where TC is equal to W by A into RC into X1 minus XC, where W is the weight of the product, A is the area of evaporation, and in this question W by A is already given directly. RC is also given. You have what is X1, you have what is XC. But all of these are in wet basis, so you will be converting it to dry basis and then substituting it inside the formula. And for the falling period, if you remember, the equation is W by ARC into Xc minus Xc, which is the critical moisture content minus the equilibrium moisture content, into ln of x1 minus xc by x2 minus xc. So we have all the parameters, it's just that all of those are in wet basis. So in order to convert moisture from wet basis to dry basis, this is the formula. So moisture content in the form of dry basis is equal to amount of water vapor. So when you talk about dry basis, it is amount of water vapor by amount of dry solid. If it is wet basis, it is amount of water vapor into total amount of the solid. That is the difference between dry basis and wet basis. Is that clear? In dry basis, your denominator will be the dry solid. In wet basis, it will include the dry solid plus the water vapor. So in order to calculate the x dry basis, that is equal to x in wet basis divided by 1 minus x in wet basis. So x1 in dry basis is equal to 0.35 into 1 minus 0.35, which is 0.5385. Xc is 16%, which is 0.16 by 1 minus 0.16, which is 0.1905. Similarly, x2 is 12%, which is 0.12 by 1 minus 0.12, which gives me x in dry basis, which is 0.1364. And Xc is 4%, which is 0.04 minus divided by 1 minus 0.04, which is 0.0417 kg of H2O per kg of dry solid. I hope this is clear. Is there any doubt in the definition of dry basis and wet basis? In dry basis, your denominator will be amount of dry solid. In wet basis, it will be amount of dry solid plus amount of water vapor. That will be your denominator. So now that you have all the moisture content in dry basis, it is just basic substitution inside the equation, where the total time is equal to time due to the constant rate period plus time due to the falling rate period. So W by A is already given as 2.25 kg per meter square, and I am substituting RC as 5 here, and X1 XC directly from what we have calculated here as in the form of dry basis, which is 0.53 minus 0.19, plus W by A is again 2.25, XE is 0.19 minus XE, which is 0.04 by RC, which is 5, and natural logarithm of X1, which is 0.53 minus XE 0.19, X2 is 0.13 and XE is again 0.04. This is just basic substitution that we have done here. Everything else is given in the question. So we get the total time as 0.1868 hours, which is 11.21 minutes. Hope this is clear. So when given a question, first identify what is the critical moisture content, what is the equilibrium moisture content, what is X1 and what is X2. From there it will be pretty straightforward. So this is also a question that has been repeated again in the previous year assignments. Is there any doubt, any part that needs to be repeated? Okay, moving to question 16. 150 kg of paddy is dried from 21 moisture wet basis to 13% moisture wet basis. What is the weight of the paddy after drying? So this is a basic mass balance question. Can anybody tell me how to proceed with it? So let us assume this is the drying process. You have F, which is feed, which is 150 kg, and you have a moisture content of 0.21 in the form of wet basis. You don't know what is the weight of the paddy that is coming out, because a lot of the moisture will be dried up and taken by the air. So your P will not be equal to F similar to what we discussed in one of the previous questions. But you have the final moisture content given as 13% or 0.13. So in order to calculate P, similar to the previous question that we did, we will do a solid balance. So in a solid balance, let's say if 21% is moisture, the rest is the dry solid. So F into 1 minus the moisture content will give me the total amount of dry solids. Is this part clear? If 21% is moisture content, the rest is the dry solid. So 1 minus the moisture content will give me the dry solid, is equal to P into 1 minus the moisture content of the product. This will give me a solid balance. In the previous question, 1 minus MC1 was already given in the question. So you just directly substituted it as the dry base mass. Here, since moisture content is given, you will convert it into dry solids, and then you will multiply it with F. So 150 into 1 minus 0.21 is equal to P into 1 minus 0.13. From there we get the mass of the products paddy as 136.2 kgs. Answer is option C. Is there any doubt in this question or the previous question? Any confusion? If it is given dry solids, just directly multiply it with F and directly multiply it with P. If moisture content is given, convert it into dry solids by 1 minus the moisture content, and then you multiply and find out what is P. So always do a balance of the dry solids and not with the moisture content. That's what you need to keep in mind. Okay, question 17. This is also one of a lengthy problem. The 2.5 kg of air stream at 30 degrees Celsius having a humidity of 0.012 kg per kg of dry air is mixed with 1.5 kg of air stream at a temperature of 30 degrees Celsius and 85% relative humidity. So these two streams enter the dryer. The mixture is then heated to 60 degrees Celsius sensibly. The moment you have something known as sensible heating, if you remember, the humidity remains the same. Only the relative humidity decreases. That was the first question that we discussed in the problem solving session. So it is heated to 60 degrees Celsius sensibly. The saturation vapor, that is PS, at 30 degrees Celsius and 60 degrees Celsius are 4.5 kilopascals and 20 kilopascals respectively. The total pressure of the system is 101.325 kilopascals. We need to calculate the relative humidity of the resultant air. Now, since you are mixing the two streams and then you are heating the mixture as well sensibly, you will have a change in the relative humidity. That is what you need to calculate here. So, we look at a diagram here. Let's say you have the A stream, which is 2.5 kgs, entering at 30 degrees Celsius and has a moisture of 0.012 kg per kg of dry air. Then you are mixing it with the B stream, which is 1.5 kg. You do not know what is X2 there, but you have the relative humidity as 85%. X and our relative humidity are completely different concepts. Please don't confuse yourself with that. So here relative humidity is given as 85%, which is 0.85. You have a heating process happening and you need to calculate what is the relative humidity of this particular stream. So you can actually do a mass balance here to find out what is C and what is RH3. So given here A is 2.5 kgs, B is 1.5 kgs, H1 or X1 here is 0.012 kg per kg of dry air, RH2 is 0.85, temperature of the first stream is 30 degrees Celsius, temperature of the outlet stream T2 is 60 degrees Celsius, the saturation pressure at 30 degrees Celsius or of the inlet streams is 4.5 kilopascals. The saturation pressure at 60 degrees Celsius or the outlet stream, because the mixture is at 60 degrees, both these inlet temperatures are at 30 degrees. So the saturation pressure of these inlet streams are 4.5 kilopascals. The saturation pressure of the outlet stream at 60 degrees is 20 kilopascals given in the question. And the total pressure is given as 101.325 kilopascals. we need to calculate the relative humidity. So if you guys remember the definition of relative humidity, it is the ratio of the pressure due to the water vapor to the saturation pressure at that particular temperature. So relative humidity is the pressure due to the water vapor present in the stream divided by the saturation pressure. That will give you the relative humidity. So for stream B, where we already know what is the relative humidity and we already know the PS given at 30 degrees Celsius, we can calculate what is PV. Relative humidity is given as 0.85. The saturation vapor pressure at 30 degrees Celsius, which is the temperature of the stream, is given as 4.5 kilopascals, which is PS. So if you multiply relative humidity into PS, you get PV, which is 3.825 kilopascals. So from PV, it is possible to find out what is the humidity or the, of that particular stream. So the humidity can be given as 0.622 into PV divided by P minus PV. Here PV is the vapor pressure that we just calculated and capital P is the total pressure of the system. So if you know what is the vapor pressure and the total pressure of the system, it is possible to calculate the humidity of that particular stream. So I am substituting the values here. 0.622 into PV, which we just calculated in the previous step, 3.825 divided by 101.325, which is the total pressure given in the system, minus 3.825. This gives me a value of 0.0244 kg per kg of dry air. So now you know the humidity or the X2 of the other stream as well. So now you have X1, you have X2. You do not know what is the relative humidity at the other end. So since this is just a basic mixing process and heating process, you can do a mass balance equation. So when you do a total mass balance equation, since it's just mixing and you're assuming no loss, the total amount of inlet stream is equal to the total amount of outlet stream. So A plus B is equal to C here. You're not assuming any gas going out or anything of that sort. You have, so A plus B is equal to C. So that, which is 2.5 kgs plus 1.5 kgs, which will give you the total amount of steam that is going out. Since this is just a mixing and heating process, you are not having any kind of air going out or any kind of a heat loss or a mass loss at all. So you can do a direct mass balance. Had it been a drying process, yes, you will have your outlet will not be equal to the inlet. You will have some water vapor that is passing, that is going to the air, drying air. Here, since it is specifically given as a mixing and heating process, you are assuming that the air is not carrying any, there is no air that is supplied that is carrying any extra water vapor. So you have a complete mass balance that is possible. I hope there is no confusion in this. So you need to carefully look into what is a mixing process and what is a drying process. And the other mass balance that you can do is for the moisture content. So A into H1 plus B into H2 is equal to C into H3. So if you're just mixing the stream, the air streams, the total moisture content will also remain the same. So A H1 plus B H2 is equal to C H3. You already know what is A, which is 2.5 kgs. H1 is given in the question. B is also given in the question as 1.5 kgs. H2 is what you calculated here for stream B, because you calculated what was PV for the stream. From there you calculated what was H2. You just calculated what is C and we need to calculate what is H3. So I am just substituting the values. 2.5 kg into 0.012 kg per kg of dry air plus 1.5 kgs into 0.0244 into kg per kg of dry air. So this is the inlet moisture content that is equal to the outlet moisture content, which is 4 into H3, which is still not known. From this, you can calculate H3 as 0.0166 kg per kg of dry air. But what is asked in the question is the relative humidity and not the absolute humidity. So H stands for absolute humidity and RH stands for relative humidity. So from this, you have to back calculate the relative humidity. So the same equation can be followed. So you have what is H, you have the total pressure of the system. From there, you can calculate the PV of the outlet stream. In a sensible heating procedure, since the humidity remains the same, you are substituting the value of the humidity as 0.0166 is equal to 0.622 into PV divided by P minus PV. The total pressure remains the same for the system. So from this, you can calculate what is the PV of the outlet stream. So we're just back tracing again. From initially we had the relative humidity. From relative humidity, we calculated the absolute humidity. Now we have the absolute humidity of the outlet temperature. From that, we'll back calculate the relative humidity. So we have PV here as 2.635. So from PV, we can calculate what is the relative humidity, which is PV3 minus PS3. And we know what is the saturation pressure at 60 degrees Celsius, which is given in the question. I think there's a small error. It has to be 20 kilopascals. So I'll just look into this again, but basically you just back calculate, there's a small error here. So you back calculate the relative humidity from PV3 minus PS, and that will give you the relative humidity. So I hope this is clear. There's a small error in the question, I'll rectify that. So you divide it by PS, which is given here as 20 kilopascals. So hope the technique is clear at least. From relative humidity, you calculate the humidity and then you do a mass balance to find out what is the humidity of the outlet stream. From there, you can back calculate the relative humidity. I look into it and get back to you with the answer here. So question 18, and the last question here. The food product of 12 millimeter thickness is dried from 35% dry basis to 14% dry basis by flowing hot air on both the sides of the slab. What is the time required for drying if the average diffusion coefficient moisture in a product is 10 into 10 power minus 6 meter square per hour and the equilibrium moisture content is 4% by dry basis? So the moment you have average diffusion coefficient given in the question, you cannot assume it to be a constant drying process. It is in fact a falling rate period that is happening. In the falling rate period is where your diffusion starts dominating, and that will result in the fall of the drying rate. So when you have the diffusion coefficient given here, let's say the slab thickness is 0.012 meters. X1 is 0.35 dry basis, X2 is 0.14, diffusion coefficient is given as 10 power minus 5 meter square per hour, and the equilibrium moisture content is 0.04. So what is critical in here right now is that we need to find out what is the direction of the hot air flow. So the hot air is flowing on both the sides of the slab. So with that in mind, let us look into the falling rate period if diffusion is what is affecting the process. Here it is nowhere mentioned that it is a linear dependence, and since diffusion coefficient is given, you will not use the previous formula that we've been discussing. You will use this particular formula that is derived from Fick's law of diffusion. So Tf is equal to 4a square by pi square d into ln of 8 into x1 star by pi square x2 star, where a stands for characteristic length, d stands for the diffusion coefficient, x1 star is x1 minus xe, and x2 star is x2 minus xe. So based on the direction of the hot air flow, your a will vary. If you have the hot air flowing only on one side of the slab, your a will be the total slab thickness, which is 12 millimeters. If you have the hot air flowing on both the sides as in the question, a will be half of this. So the characteristic length a will depend upon the direction of the hot air flow. If it is on one side, you will consider the total thickness. If it is on both the sides, you will consider only half the thickness. So x1 star is x1 minus xe. Since both of these are already given in the dry basis, we can just directly substitute it, which is 0.35 minus 0.04, which is 0.31. x2 star is x2 minus xe, which is 0.14 minus 0.04, that is equal to 0.01. So I am directly substituting it into the equation. 4 into a, which is half of the slab thickness, 0.006 square, by pi square into d, which is 10 power minus 5, ln of 8 into x1 star, which is 0.31, by pi square into x2 star, which is 0.01. This is just simple substitution of the inside the equation. From there you get the Tf as 1.34 hours. So the answer is option A. So if diffusion coefficient is not given, you can assume it to be a linear dependence falling rate, and you can use the previous previous equation that we've been discussing. If the diffusion coefficient is given, you cannot entirely assume it to be a linear dependence. So you will use the Fick's law of diffusion. You will use this particular equation, which is derived from the Fick's law of diffusion. So hope this is clear. So with this we conclude the particular week's problem solving session. I will get back to you with this particular problem as to why there's a, instead of PS, why we are dividing it by the total pressure. But apart from this, is there any doubt? Kindly let me know. Any doubt so far? If not, then we can wrap up today's lecture.
Thank you, ma'am. Thank you.